Okay, second part of this video. Let's try it the way that is described in the TCMS book. Okay, I kind of like this picture. This is the kind of describing what's going on. They use different variables for things, but it's basically the same kind of thing. And I think the other book called this, was it R? Yeah, I think the book called this R. Anyway, these are the things that are broadcast to everyone. This is the thing we're going to be using as the mod number the whole time. And this is the exponent that people are supposed to use to raise their code basically to this power before they do this mod and before they broadcast it. So yeah, so the inherent kind of magic about this whole thing is that everybody knows this key. Someone comes up with a message, they use this to encode it, and people can't take it apart. Like anyone else who intercepts that encrypted message isn't going to be able to take it apart without knowing essentially what this D is. Notice in the end on the other one, we never used P and Q to take this number apart. We used the D. That was also, again, part of the sort of number theory magic about that. Okay, wow, this is way easier to read than the other one because it's on a scan. Okay, so construct the keys. Now we are the receiver at this point. We are the people kind of at the bottom of this thing right now. We're the person who's going to publish the key. And again, when the person publishes a key, they make the key public, they're saying, okay, you use this public key to encrypt your message and send it to me, and I will be the only one who can understand it. And that's how the encryption is kind of based. Okay, choose two prime numbers P and Q and compute N. Okay, let's pick some numbers. Okay, I decided to pick a little bit bigger numbers this time just to keep it interesting. I didn't want to pick numbers that are right next to each other, like they're not consecutive primes. Let's go with that. And as I think of this, as I'm getting smarter as I do this again, I will copy paste things in from the calculator so you can kind of see what I'm doing. Okay, so my N here is going to be 1961, which is the same upside down, which is kind of cool. And I use those primes. Okay, so now compute this thing. I think they had another variable for this in the other version, but I'm not going to worry about that now. All right, so it's P minus 1 times Q minus 1. So that would be 36 times 52, and I'll copy paste that in as well. Okay, so that's what I just kind of tried to show here right below that. We're going to call this thing now R. All right. Well, they didn't use R in their graphic. Now we have an R all of a sudden. Okay. Choose a number for, oh yeah, it wasn't R, it was S in the other one. Sorry, now I remember which one's which. Choose a number E for encrypt. Oh, that's helpful. Such that E has a multiplicative inverse in ZR. Now that was explained slightly differently in the other video, in the other process. Okay, I'll stop comparing them. Let's just do this. Choose a number E such that E has a multiplicative inverse in ZR. Well, that just means that, okay, so it's an E in ZR. Of course, we're modding by 1872. By having a multiplicative inverse in ZR, that basically means that there's going to be another number under 1872 such that when I multiply them, they will make a product that is 1 mod 1872. So it'll either turn into 1873 or some equivalent to that mod 1872, which I believe is exactly the same thing as what they said in the other one, which was pick a value that, just a second, when you raise it to some consecutive power. Remember, we were raising that number to consecutive powers until we found it when it modded down to 1, and then the previous power was the same thing. So that's kind of the same thing here. Okay, so I think that's really easier said than done. I kind of used the other book's method to cheat to figure that out. But I chose a number E. I chose my E to be 25. It's something that has to be in the set that's available elements for ZR, so it's got to be less than 1871. I picked the number 25, and I cheated. I used 25. I'll show you what I did. I used 25 because it does not have any common factors with 1872. But I did use this book to show why this is going to work. Anyway, so I picked a number that didn't have anything in common with 1872 factor-wise. I did their little trick that they showed before where it's like you take successive powers and mod it 1872 until it eventually turns into 1, which it did here at the 6th power. Then that tells me that 1273 is the multiplicative inverse. If you don't believe me, watch what I did here. If you multiply 25 times 1273, you get some crazy number, but you mod that 1872 and it becomes 1. So I said I cheated by using the For All Practical Purposes book method to figure out what this number should be. But when I did that in the For All Practical Purposes book, I never realized that what I was actually doing, and they never told me, what I was actually doing there was finding multiplicative inverses. So what I don't know is, and you'll have to help me and we'll have to look in the book, is there anything in the TCMS book that describes how to find multiplicative inverses, especially when these things get kind of big? So I just determined, and I think this is kind of cool, that 25 and 1273 are multiplicative inverses in the mod 1872 world. So D here is 1273, and I'll copy paste in there how I did that. So again, I looked at the factors of 1872. I found out that there wasn't any 5s in there. Just to be interesting, instead of picking 5, I picked 25. I thought that might help me find a multiplicative inverse sooner. I don't know why. I could have picked 125. I could have picked 5 times, I don't know, 7, like that would have worked, because I could have picked 35. Anyway, so I started taking that number 25 to successive exponents. I went all the way to 6 before I found that it was going to turn out to be 1. And then to figure out what that multiplicative inverse was, I backed up a step. And that's exactly what they told me to do in the other book. So that's how I kind of cheated using the other book. But now that I've found that, I know that 25 and 1273 are multiplicative inverses in ZR. Okay. Because the next thing I showed in the calculator there was, because if you multiply those two numbers, you get 31,825. But then mod 1872, yes, that does turn out to be 1. Okay. Publish E and N in the public directory. So 25 is the number they're going to be using as exponents, and 1961 is the modding they're going to be using. It's associated with the individual who constructs the keys, but it can be used by anyone. So anyone can use that to encrypt their message, but no one else but me will be able to, because I know about this 1273, and I know about this 1872. Actually, anyone would know the 1872, but I'm the only one who knows about the 1273. Yeah, actually, no one else would know about the 1872, because to know about the 1872, you had to know about the 37 and the 53. And this is the biggest part of the secret, really, that I'm the only one who knows how to factor 1961 into primes. That leads to the 1872. That leads to the 1273. Anyone else out there is going to know, okay, I need to find the multiplicative inverse of 25 in some mod universe, but I don't know what universe that is. So that's not going to be helpful. Okay, keep D and P and Q all secret. You're not going to use P and Q, but if someone else had them, they could reconstruct these steps. So that's why it's a very secret thing. Okay, this one just says convert the. Oops, sorry, made another mistake. Had to go back. Convert the plain text message, including spaces, into these numbers. Now this one doesn't say we're going to break them up into like strings of longer strings of digits. It just says kind of keep each letter separate, essentially, into numbers, so that each number goes into something in the Z mod N world. And again, we're back to the 1961, the published public key number 1961. Okay, so I'm just going to convert those into numbers. O L I N G. And that's all it's telling me to do right now. So I've just got those as numbers. Raise each number to the power E. Sorry, I moved some stuff around. Raise each one of these numbers to the power E. So I'm going to take 12 to the 25th power. I'm going to take 14 to the 25th power. This gets very big very quick. 12 to the 25th power, 14 to the 25th power. Like, these are huge. Let me copy paste them in. Now the beauty of our calculator, here's where I had that little etc. you may have seen earlier. Sorry about that. The beauty of our calculator is we don't have to actually look at these, because the only thing I'm going to do with this, I don't really care about the value of this so much. I care about that mod N. So let's go straight to mod N, and of course N is 1961, but on the calculator we can just do that kind of immediately. I could do that in one step. Mod 12 to the 25, I'm not even going to go to the answer, 1961, and it'll just tell me that right away. And I can do the same thing with 14, and I can just kind of copy paste my way through all of these. I will do that. All right, so here's all these grabbed off the calculator. So the encrypted message becomes these 8 digits, these little strings of digits. Again, I think we have to keep the kind of the spaces or the commas between each one of those. So in the end, this is the message we're going to send. All right, so now we've received this message. We are now, again, the part of the key maker, the person who's supposed to be receiving this message. They received this message, and it's time to decrypt it as only we can. Raise each one of these numbers. So again, I think that I keep saying this, but this kind of implies to me that these have to be received as separate numbers and not one big string. Raise each one of those numbers to the power D, which is this 1273. Okay, let's do that. And while we're at it again, so because I'll be taking 1082 to the power of 1273 mod 1961. If we do that all in one step, the calculator doesn't love us, okay? Because we're taking 1082 to the 1273rd power and then mod 1961. The calculator say, well, 1082 to 1273, the calculator finally does give up on us and say, okay, that's basically infinity and that doesn't make sense. So we'll have to do what they said in the 4-app book, which was, let's split this 1082 to 1273 into two factors, and then let's try to mod those separately and then mod that product, and that would be a smaller job. Well, the problem is, yeah, that sounds great, but then you even do this even as a smaller version. Like I could do this as like a 673 times, let's say I did that with like the power of 600, because those add up to 1273, and guess what? It's still too big. Notice it's just saying squared now. It's kind of funny. So I really got to break this down. Let's see how small I need to make this, and let's actually just do one term at a time. This is starting to get kind of creative. Can I do 373? No. Can I do 273? Okay, I can do 273. So if I wanted to break this up into smaller chunks, I could do that times, so I still need to do another 1,000. I'm guessing it'll do mod 1082 to the power of, let's say 200, 1961. But then, because that's only 473, I kind of need, 5 copies of this? So I'll take this whole part to the 5th power. Okay, now I'm getting a little bit creative. But it works, and I get that giant number, but it's not saying infinity. It's not copying out. So I need that now reduced mod 1961. And guess what? It's 12. Well, the good news is I needed it to be 12, so that worked out great. Let me copy paste in here from the calculator kind of what that process was about. And let me talk through it. So it says raise each ciphertext number. So I'm trying to take 1082 to the 373 and mod that 1961. When that happens and the calculator doesn't like it, we have to split that up. When I had to change the view on the calculator so you could see that. Anyway, I had to split this big number, because this was the problem, it was too big. I had to split it up into that times 5 copies of that. Notice I did the little 5 there. So that all still kind of multiplies back together and makes, what? Oh, this is a problem not even at 373. This is a problem at 1273. Sorry, it was a problem at 1273. I was checking it later and it was a 373 problem. It's even a problem at 373. Anyway, it's supposed to be 1273, remember, because 1273 is the number I need for D. So to figure out what this is, mod 1961 for this giant number, I split the 1273 into 273 plus 1,000, but I couldn't do 1,000, so I did 200 5 times. Anyway, that all worked, and I got an actual number. Then I could mod that, and if I modded that, it actually came out. Switch back to the mode you probably like seeing it in. So I went ahead and did that mod 1961, and I got 12, and 12 is the number I wanted back from the original, pre-encrypted message. So doing that with all 8 of these numbers is going to work. If you don't believe me, here's that exact same process with the 458, and yes, it turns out to 14. So that gets us our original message back. I don't have the energy or time really in this video, or the motivation to do all 8 of them, but we can do this in class. And then convert back to letters, fine. I really don't understand this instruction. Reduce mod n, didn't we do that back here? And why would we do that after we have letters? So I think this is actually a misprint. Let's just get rid of that. Okay, and then I think we're done. All right, I'll see you in class. And we'll talk about, why does this work? Okay, bye.